Good morning, all you cool cats and kittens. We are first going to review some alcohol chemistry, and then we're going to learn something new with alcohols. So let's first just review what we know already. So for Bronsted acid-base reactions, we know we can take an alcohol and we can add a base to it. I'm going to use a strong base, sodium hydride. Remember, when you see sodium, here you're going to be having an ionic bond, right? So we have a strong base. We're going to deprotonate that alcohol, okay? So here we go. We deprotonated the alcohol. And the second step of this reaction, we're going to be adding in an alkyl halide. This is that Williamson ether synthesis that we've talked about before. So the first step here, so step one, we're making our alkoxide. Now notice that this stereocenter here didn't change, okay? That stereocenter is still coming out towards us there, okay? So we have our alkoxide, and then we're going to do our step two, which is adding our alkyl halide. This is essentially just an SN2 reaction. So step two here is this SN2 type reaction where we take our alkoxide, attack the alkyl halide, and then we get our desired product, which is this ether. So alcohols can be used to make ethers. One of the important parts here is, although we did an SN2 reaction, remember that the stereocenter here did not change. We didn't draw any arrows to that. We simply took our oxygen, and now we've added 2 carbons. The SN2, we know, does invert, but it's at this alpha carbon, and there's no stereocenter there. Just a little reminder about that. Let's also review something else that we've talked about with alcohols, and that we know that alcohols under strongly acidic conditions can do an E1 reaction. These strong acids that we use are non-nucleophilic, okay? So these are acids that don't have a nucleophile. Say, for example, HBr, that would have that Br nucleophile. So these are, for E1, these are non-nucleophilic acids. Something like HBr would be undergoing an SN1 reaction. All right, let's do the mechanism here. So we've got H2SO4 and an alcohol. We know that our first step is going to be protonation. And we've drawn this enough to where I'm going to skip the arrows for the protonation, but you might want to draw them in. We have our hydrogen here, and we've added one more hydrogen, okay? So I'm going to write H plus over that arrow. So we've protonated our alcohol. We've made a great leaving group, and we're going to kick it out. So alcohols can be turned into leaving groups. Here we make a carbocation. Now that carbocation is flat, right? Now, when we're looking at this, we need to see if we have a beta hydrogen. So our alpha carbon is on that carbon with the leaving group, and our beta hydrogens, our beta carbons are right here. Do we have any beta hydrogens? Well, we do. We have 2 here, and we have 1 here, okay? And when we're thinking about an E1, remember that this is under thermodynamic control. If it's under thermodynamic control, that means the most substituted alkene will form. And so we are going to take our hydrogen from this beta hydrogen on the bottom here, and that would make the most substituted alkene. So let's take the conjugate base of our acid from our sulfuric acid, and we're just going to deprotonate here. Okay, take this proton, fold the electrons down to form the alkene. Now, these are reversible steps. And this forms our desired alkene. Now we don't have stereochemistry now at the alkene. Remember, alkenes are flat. And so these are two reactions that we have seen before. This is just review. Now, in addition to E1 reactions, we've also learned how to do SN1 reactions with alcohols with HX. So let's take this tertiary alcohol and we're going to do an SN1 reaction. Let's react it with HBr. Again, this part here is review, but it never hurts to go over mechanisms again. I think that's the only way you can really get accustomed to writing them out and using them. So here we have made a good leaving group out of that alcohol. We're going to make it leave. This reaction is, all the steps are reversible. We have a tertiary carbocation, and then we're going to take our Br minus. We're going to attack. Now this HX is a different kind of acid that is going to give us the SN1 product because we have this Br minus that is our nucleophile. Now, if we think about our previous slide where we were doing the E1 reaction, notice we were using a non-nucleophilic acid. It's kind of the key here. All right, so now we've added our bromine. Cool, so this is happy. This is our review for that SN1 reaction. We've also done SN1 reactions with secondary alcohols. Let's use HBr again. I'm going to protonate. I promise we're getting to something new at the bottom of this slide. All right, so we've protonated here our alcohol. We have our leaving group. We're going to make it leave. And we have a secondary carbocation. Now this was optically active, but notice now we have a flat carbocation. These are achiral, and that our bromine nucleophile can attack from above or below. That means we're going to get two products here. So we're going to get the bromine either above or below, and you can do this by writing this out here and just write racemic. I'm going to show you a little trick here. When you see your leaving group, and it's this alcohol here, when you see the alcohol, you can simply just replace it with the Br and then write racemic if you start with this optically active compound. Now, another way you could do it is you could also draw it with the bromine wedged or dashed. Just make sure that two of the lines on your chiral center are in line with the piece of paper. All right, here is the new thing. This one is a new, it's pretty much a new reaction. It looks very similar. We have a primary alcohol. This is not going to do an SN1 reaction. It's going to do something very similar though. Still substitution. We're going to take this alcohol and we're going to protonate it. Now, why can't this do an SN1 reaction? When we look back at the previous SN1 reactions, we've made carbocations. This was a tertiary carbocation, and here we have a secondary carbocation. And so in this case, you can't kick this out to form, here, don't draw this, I'm going to erase it, but you're not going to form a primary carbocation. That would be very unhappy. So instead of making a carbocation, what happens is that this protonated alcohol kind of waits around, and this Br minus can attack and do an SN2. Now, part of the reason why it can occur on this substrate is because this is not very hindered. It's primary. This alpha carbon here is primary. It's unhindered. So when we think about these primary alcohols, we are going to be doing an SN2 type reaction in the presence of HX. Now you still get the same kind of substitution product. We've added our bromine here. I wanted to highlight in this video some of what we've already learned with alcohols, and we're going to be looking more into alcohols this week in these videos. This new reaction we've learned is simply just a new reaction pathway for one specific type of alcohol. But notice how similar all these things are, even on our previous slide. We're using acid-base chemistry a lot of times to affect chemical change on alcohols. And on the bottom of the slide, we were doing an E1 reaction here. And this E1 reaction was also making this carbocation. All we did was just change the acid so it had a nucleophile. Now, if you have a primary alcohol, it can't make a primary carbocation. So some of you might have guessed that this was the mechanism without me even telling you. This is what's really neat about organic chemistry, how things kind of stack up, and they all kind of make sense when you think about the fundamentals. If you can make a secondary or tertiary carbocation, you're good, but if you can't, and if this is primary, this can't undergo SN1. It would have to undergo SN2 chemistry. All right, that's it for this video, and I will see you in the next video.